In this video, we'll be covering DeMorgan's law. So let's take a look at it. You can think about DeMorgan's law as informing us how a negation can be distributed among the content of a parentheses that it's attached to, when what's within the parentheses is a conjunction or a disjunction. Now, that's not technically correct. It's not that you're actually distributing the negation, because we have to change some signs around, but it can be helpful to think about it that way. So notice here in this first instance of DeMorgan's law, what this sign tells us is that these two are logically equivalent. They're going to have the same meaning. And in fact, we can even prove that by using a truth table. So we can make a joint truth table. We're going to have to worry about P and Q. One of our sentences is not the case P and Q. Our other sentence is not the case P or not the case Q. We're going to have 4 rows since we have 2 sentences in our reference column, P and Q. So TF, TF, and then double that pattern as we move to the left, TT, FF. All right, so since this negation is attached to a parentheses, the conjunction that's within the parentheses, we have to figure out the truth conditions of the conjunction within the parentheses first. And we said that the truth conditions for a conjunction is true if and only if both of its conjuncts are true. Otherwise, it's false. And there's only one situation, namely the first row, in which we get both of the conjuncts to be true. So here, it's true, and in the rest of our cases, 2, 3, and 4, we get false. Now, that's what's being negated. This right here is what's being negated by this negation. So since we're saying that that conjunction is false, we're wrong in case 1, because it's actually true in case 1, but in all the other cases we're right. So those get T's. All right, and so that's the truth condition for that sentence. We can do a truth table then for the sentence on the right. Here we have 2 negations that are being connected by a disjunction symbol. So I can't figure out what the truth conditions of this disjunction symbol is until I figure out what the truth conditions are for these sentences that are negated. All right, so since our P in our reference column is TTFF, and this is negating those, we flip the truth values around, and we get F, F, T, T. And since our Q is TF, TF, and we're negating that, we put in the opposite truth values, so FTFT. And the truth conditions for a disjunction, we said that a disjunction is true if and only if at least one of its disjuncts is true. Otherwise, it's false. Well, in our first case, we don't have at least one of our disjuncts to be true. So it gets the value false. In this case, we do have one of our disjuncts being true, so it's true. Here we have a disjunct that's true, so it's true. And they're both true here, so at least one of them is true. That's true. Now, if we compare the columns of these 2 sentences, we see that in situation 1, they're both false. We see in situation 2 they're both true. We see in situation 3 they're both true. And we see in situation 4 they're both true. They mean the same thing as far as FOL is concerned. They have the same truth conditions. All right, so looking at the patterns then here, what it tells us, what we can infer from it, is we can distribute the negation out in front of the P and the Q so long as we change the conjunction symbol to a disjunction symbol, in which case we'll know that we have a logically equivalent sentence. So we can change those sentences out and preserve the truth value. That is, it would be a valid inference to move between one or the other since they say the same thing. Likewise, this goes in the reverse direction as well. We can, as it were, take these negations out to the front as long as we switch the disjunction symbol to the conjunction symbol, leaving us with this sentence. And again, that'll be logically equivalent to this one, and therefore a valid inference, a truth-preserving inference. All right, so one of the things to recognize is that P and Q here are acting as variables that range over indie sentences, including complex sentences. So DeMorgan's law just works on this pattern, whatever P and Q end up being. So let's say P ended up being not the case R, and Q was, let's say, G or H, whatever those sentences mean. Okay, so this sentence that we're looking at here takes this very same pattern, where not the case R is our P, and this disjunction G or H is our Q. So as long as we make sure to keep the sentence that we're substituting in for the P, which is our not the case R, and our sentence Q, that's taking the Q, the either G or H, then that'll be a logically equivalent sentence. So we distribute this negation in here and here, and switch the conjunction symbol out to our disjunction symbol, and we end up with a sentence like this. And that sentence will mean the very same as the previous sentence that we started with. So keep in mind, all we're looking at here is the patterns by which we can use DeMorgan's law on to get ourselves a logically equivalent sentence. All right, let's look at this other instance of DeMorgan's law. All right, so this other instance of DeMorgan law looks very similar to our previous instance, except instead of the conjunction sign, we're starting off with a disjunction sign, and then we're ending up, instead of a disjunction sign, to a conjunction sign. So if we think about it in terms of distribution again, which again is not technically correct, but if we think about it in those terms again, then we see that what we're doing is we're distributing this negation, right? But we're then changing our disjunction sign to a conjunction sign. And in doing that, we will have a logically equivalent sentence. So it's a good inference to move back and forth between sentences that take on these patterns. So whether we're making the inference from here to here, or whether we're making the inference from here to here, it'll be a truth-preserving or valid inference. And we can show that these are logically equivalent by using the truth table just in the same way that we did last time. So we have our reference column, which will include P and Q. We're going to have 4 columns then, because 2 to the second power is 4. Our first column always takes the true, false pattern. And then as we move leftward, we always double that, so we get true, true, false, false for our P. One of the sentences we want to determine the truth conditions is that one, and then we also want to determine the truth conditions of this sentence. All right, so in this first one, we have a negated disjunction, which means we've got to figure out the truth conditions of the disjunction before we can figure out the truth conditions for the negation. We said that a disjunction is true if and only if at least one of its disjuncts is true. Well, there's only one case in which it's not the case that at least one of their disjuncts is true, and that's the fourth case. Situation 1, 2, and 3, we have at least one of the disjuncts as being true. All right, so then in our negation, it tells us to just flip those truth values around, since it's saying that it's false. So when it says that something is true, when it says something that is true says of it that it's false or wrong, and so we get the value of F in those cases. But when we say of something that's false that it is false, we're right, and so we get a T for that case. All right, so that's the truth conditions for our first sentence. In our second sentence, what we have is a negation where both of its conjuncts are, we have a conjunction in which both of its conjuncts are negations. So we have to figure out these negations before we can figure out the truth value, the truth conditions of our conjunction. So for not the case P, we just flip out the truths for false and the false for truths. And for the Q, we do the same thing. Oops. There we go. And a conjunction is true if and only if all of its conjuncts are true. So if we have one case in which a conjunct is false, or when both of them are false, we get the value F, because then then the sentence is false. Only when both of its conjuncts is true does it get the value true. Well, this is the only case. Case 4 is the only case in which both of the conjuncts end up being true. So all these other cases, case 1, 2, and 3, end up getting the value false. So then we compare the truth conditions of our two sentences, and we see that they're the same. In case 1, they're both false. In case 2, they're both false. In case 3, they're both false. In case 4, they're both true. So they mean the same thing in FOL. All right, and that's why we can then, since they're logically equivalent, since they mean the same thing, that's why it's a valid inference to infer one from the other. Again, to reiterate, what we're worried about here is the pattern that's taking place between these two, and that's what allows us to know that inferring one from the other is a good inference, a truth-preserving one or a valid one. So it doesn't matter P and Q being variables. It doesn't matter what sentence they're actually representing, even if they're compound sentences. So, for instance, if we let P be the sentence D and F, so if we let that be P, and if we let Q be, say, not the case C, then if we found a case in which we had a sentence such as this, that takes the very same pattern that we have here. That takes the same pattern as this. Okay, so in terms of distributing the negation, then, where we can distribute these to the two sentences, and then make sure to change our disjunction symbol to a conjunction symbol, we know that this would be, from this sentence, this would be a valid inference. Okay, and again, that's just to stress that all we're worried about here is a particular pattern. That's what using the variables P and Q, that's what that's supposed to be capturing there. So just know that whenever you can identify that pattern, you can move from one or the other and preserve the truth value. All right, before wrapping up this video, I want to talk a little bit about how reflecting on what's being expressed in these sentences can lead us to understand that they're expressing something logically equivalent, that they're saying the same thing. So looking at this sentence first, it's saying not the case both. And you think about not the case both. When is somebody right when they say not the case both? Well, they're right when this is either false, this is either false, or both of them are false. That's when you get not the case both. And then you think about what this says, and it says either this is false or this is false. And since it's the inclusive sense of the disjunction, it means to say when it's right when this really is false, this really is false, or when both of them are false. And that's just what this was saying, right? So just thinking about that, what's being expressed can lead us to that realization. We get the same thing here. This says not the case either. Not either of those. And when somebody says not either, what they're saying is both of these are false. Right? You're only right when both of those are false, when you say not either. And then when you think about this, it just is saying that this and this are both false. false. So this is right just at the same time that that's right. So even without appealing to truth tables, just by thinking about what's being expressed, we can come to the realization that these are logically equivalent sentences. All right, that concludes this video on DeMorgan's law. I hope you found it useful.